The name of this video is Ohm's Law Local. First of all, we know that if we take a conductor in macroscopic electrostatic equilibrium conditions, let's say the conductor is this object here, which occupies a volume capital omega with a bounding surface capital sigma. We know that under these conditions of macroscopic electrostatic equilibrium, MEE, in this case, we know that the electrostatic field, the electric field, at each point inside this conductor has to be equal to 0. So in this case, we cannot have an electric current. In order to have an electric current, we need to be outside these equilibrium conditions. And so at the very least, we need to have a non-zero electric field E, different than 0, at the points capital P within this conducting object, so that there is a current inside this object. As it turns out, this is the very least you need. You need an electric field which accelerates the electrons, therefore allowing a current J with vector density J or intensity I to flow inside this object. However, as it turns out, as we shall see in one of the next videos, only having an electric field is not sufficient. It's necessary, but not sufficient to establish a current. So we need actually, in addition to that, also another quantity, which is called an electromotive field EM. We will see this in another video. This electromotive field is of non-conservative nature, non-conservative. So we need also a non-conservative field that allows us to establish a current. By means of these two fields, we obtain a vector J, density J, and therefore also a current intensity I, different than 0 inside this object. Now, from experiments, it so happens that under stationary conditions, which of course is what we are considering in this course, in 242, so for stationary currents, the fundamental laws of electrostatics are still valid also in this specific case. That is, in integral form, the circulation along any closed line gamma within this object of E dot TdL has to be equal to 0, irrotational property of the electrostatic field. In addition, we also know that Gauss's theorem has to be true, so the flux through this closed surface capital sigma of E dot mdA has to be equal to the total charge contained within capital sigma divided by epsilon naught. And in addition, we also know the continuity equation in stationary conditions implies that J is a solenoidal vector field, so the flux of J dot n dA has to be equal to 0. So this is the integral form of Maxwell's equations for the electric field under stationary conditions, and of course you can also write the differential form associated with those. However, I always prefer to write the integral form because it is more general. So it's my favorite form. Okay, great. So now we have all this set of Maxwell's equations for the electric field, electric and not electrostatic anymore in stationary conditions though. So is this sufficient to characterize an object where there is a current? The answer is no. So what else do we need in order to fully characterize the physics of this object is a so-called constitutive relation, which is fundamental in this case. It's very important. And so as we shall see later on, for each circuit element, resistors, capacitors, and inductors, we have constitutive relations. In the case of conductors, we didn't really go into that because we didn't study dielectric materials yet. We'll introduce suitable constitutive relations for capacitance, if you want, in 342 when we'll discuss about dielectric materials. Now here we are discussing about, in Ohm's law, resistance, which is one of the three circuit elements of fundamental importance. And so in this case, the constitutive relation is Ohm's law. And eventually, we're going to see also constitutive relations for the magnetic field and inductance. Okay. So now, what is the constitutive relation in this case? What does it mean? What are we seeking here? What are we looking for? Well, we are trying to find a relationship which relates these two quantities, J and J is caused by what? By E. So we want a function of the electric field E that gives as a result J. So we want a relationship between G and A. Here, in these Maxwell equations, we do not have such a relationship. We need to link all these equations by means of such a constitutive relation. Now, suppose that we consider a very complicated anisotropic material. So, for example, this could be made as an example. You could do an anisotropic material by means of MBE, molecular beam epitaxy, and you grow aluminum by means of, let's say, MBE or many other materials. This results in anisotropic materials. Okay. In these anisotropic materials, direction matters. So we know that these materials are made of ions, which spanning a lattice, a periodic lattice. So you have different directions, different orientation of all these atoms. If you can actually distinguish between this direction and this direction, then as an observer, you can tell that this is not isotropic, it's anisotropic. So in the case of anisotropic materials, the relationship between J and E is pretty complicated. So you can write it down in vector form as follows. So you can write it, for example, as in a Cartesian coordinate system, Jx, y, and z. These can be written down in this form. So there is now, I'm embedding and encoding all the knowledge I don't have of this function f in some coefficient. Let's call it a small s. So this will be s x, s x, y, s x, z. And then we go here, it's going to be y x, y, 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 z. And finally, zx, zy, and zz. So we have this matrix, this 3x3 matrix, and this finally we need to multiply times the Cartesian components ex, ey, and ez. So this is fairly complicated also because I still didn't delve, I will do this in a minute, on the functional dependence of these S coefficients. All right, so this one is actually a tensor. It's a second order tensor right there. So for anisotropic materials, very complicated. You need to use second order tensors with some very complicated functional dependence of these S on parameters. What parameters we will see now in a simpler case. What is the simpler case we are going to consider in this course, which is very common, is isotropic materials. So isotropic materials, for example, if you take an E-beam, an electron beam evaporator, or a thermal evaporator, where you heat up a piece of aluminum and this evaporates over a silicon substrate, somehow aluminum. In this case, you don't make like MBE, you make a non-isotropic material. So for example, let's say thermal evaporation is a typical example that results in isotropic materials. From Greek, isotropic means if I'm within this object and I'm an observer and I observe in this direction, this any angle in the solid angle, I always see the same or the same kind of material. So I cannot distinguish between directions. Okay, so this typically stems from the randomness of the domains of a metallic material. Let's say. So, for example, typically I can have materials where I have some grains which look like that. And there is another grain, and there is another grain, and more grains, etc., etc. Each of these grains is actually well oriented, so you can have, let's say, it's anisotropic. So each of these grains can be anisotropic, but when you have many of them together, all together, they sum up randomly to an anisotropic material. Okay. For example, also sputtering is another technique we use in our lab to make devices that also resulting in isotropic materials. Okay, so now that we know that, as a matter of fact, Feynman does a good analysis of these kind of materials in the second book, I believe. So now that we have that in hand, how does he simplify this relationship here in the case of isotropic materials? Well, it simply becomes J, it's much simpler, it's not a tensor anymore, is some coefficient, let's call it S, as here. But now let's delve into the details of each of these S has the same kind of functional dependence. So it depends on what, this S coefficient. It depends on a bunch of things. The position, capital P, within the object. It depends on the pressure P of this object. It depends on the thermodynamic temperature of this object. It depends on the mass density ρm, as well as on the intensity of the electric field E. Okay? And this multiplied time E. So in this case, for anisotropic materials, at least, we end up having the J and E are parallel to each other, and there is just this function in between, which is function of all these possible parameters. Now let's make it even simpler, and let's consider linear materials. In this case, it so happens that J becomes simply equal to S. It's not function of E anymore, so I can crank up E. Of course, there are some breaking limits, so if you increase E a lot, things break and change. In this case, it only depends somehow on position, pressure, temperature, etc. Okay, but it does not depend on E anymore, on the amplitude of E. Okay, so this is inside the function, and this is outside. All right, and finally, to simplify even further, we consider homogeneous materials. So in this case, it so happens that J is just given by a constant parameter S times E, where now this parameter S is a constant, and this quantity is called the conductivity of this material. Electrical conductivity. Okay, so this expression down here is Ohm's law in local form, where the relationship between J and E is just this proportionality constant S, which is the conductivity. Okay, so now, as it turns out, I can invert this relationship, and sometimes you will see it written as E equal R times J, where this R is equal to 1 over S, and this quantity R is called the resistivity, electrical resistivity of the material. So if you have seen by any chance in some other courses the Ohm's law, you will see here the resemblance of this local form with the integral form. The integral form is the potential is equal, V is equal Ri, okay, capital R. So here we're looking at the local form of that. Instead of the potential, we look at the vector field E associated with that potential, and instead of the current intensity I, which is an integration of J, we just look at J itself. Okay, so that's the resemblance with that. So for example, just to give you a sort of idea of numbers, so if I take a copper, in the case of copper, we have that the resistivity R is approximately something like 10 to the minus 8 volt meter divided by ampere, whereas in the case of quartz, let's say, which is a dielectric material, then R is something like 10 to the 17 volt meter divided by ampere. So obviously conductors like copper, silver, gold have very low resistivity, very large conductivity, and on the contrary, insulators have a very large resistivity, very poor, very low conductivity. All right, so this is just to give you an idea of the numbers that we can have in these cases. And so to summarize here, what we studied in this video is we moved away from macroscopic electrostatic equilibrium, and so in order to establish a current with vector density J or intensity I, we need to have at least an electric field. It's not sufficient because it's conservative, think about that. You also need a non-conservative field which establishes like a battery, which makes the current possible. Under stationary conditions, we end up having the same Maxwell's equations as in the electrostatic case. In addition, we have the continuity equation for steady current, for stationary current, which is this one down here. This is not sufficient to link this equation. This set of three equations doesn't link J and E. We need to link J and E by means of a constitutive relation. Very complicated in the case of anisotropic materials, because you need a tensor of second order. But for ILH, so this is I for isotropic, L for linear, and H for homogeneous, ILH materials, and this is the same set of categories we're going to encounter for dielectric materials, and so it's and also for magnetic materials. So ILH is really critical for many things. So ILH materials, isotropic, linear, and homogeneous materials, then we end up having the relationship is just J equal S a constant times E. This is S is the conductivity, which is very large for conductors, of course, like copper. And equivalently, we can also write down in the opposite form as E equal Rj, which again is the local form of Ohm's law, where in this case R is the resistivity. And I gave you some numbers to get a sort of a sense of how big they are. And that's it.